We will do 12 problems in this video to discuss the use of the chain rule in taking derivatives of various types of functions. Before I get into problem solving, let's have a brief review of the basics of the chain rule. Let's just start with a simple looking function such as what you see here. How do we take the derivative of this? If you don't use the chain rule, then there is really only one way to do this. You multiply it out. The FOIL method maybe, multiply every term out and collect like terms. We get a 6-degree polynomial that you see here, and we take the derivative using the power rule and the basic formulas. 6x to the 5, 3 times 2, 6x squared, derivative of 1 is 0, and we get this answer. This simple idea, however, doesn't work for these types of functions that you see here. These are also powers, but we are not likely to multiply x cubed plus 1 by itself 2020 times, nor can we multiply it by itself 1/2. For these, we are going to need the chain. So we start by thinking of those powers as composition of simpler functions. There is an inside function which is x cubed plus 1. Let's call that u for short. And there is an outside function which is a power of u. In the problem that we worked out, it was u squared, but it could just as easily have been u to the 2020 or a square root of u, which is the same thing as u to the power 1/2. We use the derivatives of these simple functions. This is an easy derivative, this is an easy derivative, easy derivative, easy derivative, together with the chain rule to come up with the derivative of the more complicated functions, like the ones we had before, perhaps, or others. Now, more generally, we are looking at a composition of two functions, f and g, which we sort of label a little bit differently. We think of the inside function g of x as u, and think of f of u, f of that inside function, we call that y. And we notice that the derivatives of each of these two functions can be done separately with respect to their own variables. Derivative of y with respect to the variable u is just the ordinary derivative f prime of u, and similarly derivative of u with respect to its variable x is du dx, or g prime of x, again the ordinary derivative. So it's important to realize that we are looking at different variables. U in this first in the outside case and the x in the inside case with this notation that we have. And now the chain rule says that the derivative of y with respect to x is going to be the product of the derivative of y with respect to u, which is the function that we had up here, or the derivative rather, times the derivative du dx. This is chain rule in the Leibniz notation. It's a key feature of the chain rule that it looks as if we can cancel out the du's, but it's really just notation. There is no algebra involved here. The chain rule can be expressed in a different notation with the primes. Dy du is just f prime of u, and u, remember, is g of x. So that's f prime of g of x, and of course du dx is just the derivative g prime of x. And putting this together, we get the primes notation version of the chain rule, which sort of reads derivative of the outside function with the inside function plugged in times the derivative of the inside function. And for this reason, sometimes the chain rule is called the outside-inside. We start our problems set with the derivative that we did by multiplying out. Here we have this function which we now want to take its derivative using the chain rule. I have an inside function x cubed plus 1 because that's inside the power. The outside function is just a square function. And let's write them down in the u and y notation. U is the inside function, x cubed plus 1, y the outside function, the square function. The derivatives of these functions separately are easy to calculate. Derivative of x cubed plus 1 is 3x squared plus 0, or just 3x squared. That's du dx. Derivative of y with respect to u is simply the derivative of u squared, which is 2u. We can also plug in what u is and come up with this, because ultimately we want our final answer to be in terms of x, not u. Now we use the chain rule, which says that to get the derivative of y with respect to x, which is to say the derivative of our original function, is dy du times du dx. We put together the two pieces of the puzzle and we come up with the answer that you see here. And this answer is the same as the previous answer. You can see that by multiplying x squared times x cubed is x to the 5th plus 6x squared, which is just what we had before. We follow the same prescription to figure out the derivative of x cubed plus 1 to the power 2020. When we do this with the chain rule, the amount of effort is practically the same. There is no question of multiplying x cubed plus 1 by itself that many times. Alright, the obvious choices are as before. The inside function is u cubed plus 1. The outside function is the power 2020 function. So we write them up in brief notation. The outside power function, the inside polynomial function. The chain rule then multiplies the derivative of the first by the derivative of the inside, derivative of outside times the derivative of the inside. Derivative of u to the 2020 is 2020 u to the 2019. That's this over here. And then 3x squared is just the derivative of u. Multiplying things out, first we might as well put x cubed plus 1 for u and get this expression and multiply that 3 out by 2020 to get 60 times x squared times that to the power 2019 as the answer to our problem. Now let's do the square root problem, square root of x cubed plus 1. Because we are taking derivatives, it's convenient to write the square root as power 1/2. The inside function is x cubed plus 1, outside is the power 1/2 function. And here are the inside and outside in terms of u and y. The chain rule says the derivative of y with respect to x, not with respect to u, is the derivative of y with respect to u, but multiplied by derivative of u with respect to x. Derivative of y with respect to u is just the ordinary derivative of u to the 1/2, which is 1/2 u to the negative 1/2. Derivative of u is, as usual, 3x squared. I'll plug in the u in for the x cubed plus in for u, get this expression, and rather than leaving it like that, I'll change the power negative to a positive power and put it back in terms of the square roots. Here it is in terms of, if I take that down below, it will be positive 1/2, and then I can write that as 2 square root of x cubed plus 1, and then 3x squared times 1 is just 3x squared, and that's the final answer to this problem. The fourth problem consists actually of two problems. The first one, sine of x squared, and the second one, sine of cosine of x. So the inside function is different, the outside function is the same. The inside function in the first problem, a, is x squared. The outside is the sine function. So there is the detail. Applying the chain rule, derivative of sine of u is cosine of u. That's with respect to u, and then derivative of u with respect to x, derivative of x squared is 2x. And I can plug in x squared for u and get cosine of x squared times 2x as the answer to a. For b, the inside function is cosine of x rather than x squared, and the outside function is the same sine function, sine of u. Going with the chain rule, we get derivative of the outside function times the derivative of the inside function. Derivative of sine u with respect to u is cosine u. Derivative of cosine x with respect to x is negative sine x. Then we plug in the u and get cosine of x, and then here's minus sine of x out here as the final answer to b. In problem 5, we want to take a derivative of e to the power minus x squared. If we can think of this as a composition of the exponential function e of whatever plus whatever goes inside for 3 dots, in this case negative x squared. Alright, looking at it in that sense, then we are looking at f of g of x, if you like, or f of u. That tells us that the inside function u must be negative x squared, and the outside function then is just the exponential function e to the u. Once you get that, the rest is just formula. Derivative of y with respect to x is derivative of y with respect to u. Derivative of e to the u with respect to u is itself. And then derivative of the inside function, derivative of u with respect to x, is just negative 2x. Negative 2x being the derivative of minus x squared. And then I put in negative x squared for u, and I get the answer to the problem, negative 2x times e to the minus x squared. Now let's try and find the second derivative of e to the minus x squared. Right after finding its first derivative, remember that the second derivative is just taking the derivative twice. In other words, derivative of the first derivative, as you see here. And we already figured out in problem 5 that the first derivative is minus 2x e to the minus x squared. You'll notice that this is a product of two functions. So if we want to take its derivative, we have to use the product rule, and that's what we'll do. Here are our two functions. We can think of this as maybe a function on the left and function on the right. Use the product rule on this. We get derivative of the first times the second plus the first times the derivative of the second, just as you see here. Then let's go in and fill in the derivative. Derivative of minus 2x is minus 2 times that. Then plus minus 2x is minus 2x times the derivative of the second function. We already know what the derivative of that was from problem 5, which is just this expression here. Now we simplify this a little bit so that it looks less unwieldy. First of all, minus 2x times minus 2x is plus 4x squared. And then next you'll notice that I have some common terms. There is e to the negative x squared. We can pull that out. There is also a factor of 2 hidden in 4 here. So we pull out e to the negative x squared, we get negative 1, taking this negative into account, plus whatever is left here, which is a 2 and an x squared. And that's the second derivative, the final answer to this problem. Now let's tackle the derivative of 2 sine x plus sine of 2x. In a lot of technical writing, there are no parentheses to indicate exactly what's inside and what's outside, so let's put the parentheses in there to be clear as to exactly what this is. And here's a little bit of explanation. Sine of 2x is the function that evaluates the sine at 2x. It shouldn't be interpreted in one of these forms. This is meaningless. There is no mathematical meaning for sin. And the second one is mathematically meaningful, but it has a completely different meaning. It's a totally different function from what we have here. And if we wanted it to be this, then we would simply write it as this right up there. So if we are writing it like that, then we mean this right here. Okay, with that out of the way, we have two terms. The first term is a straightforward derivative. The second term is where we use the chain rule. There is an inside function 2x, which we can call u for short, and then figure out the derivative of the outside function, derivative of sine u. So the derivative of sine u is cosine u, and remember that u is 2x. And the first term is straightforward. Derivative of sine is cosine, so we just get 2 cosine x, and we've got the answer to this problem. In this problem, we are looking at the sine squared plus sine of x squared. Again, to be clear, let's put in the parentheses to clarify what the role of that power of 2 is. Specifically, sine squared x is just square of sine of x, whereas sine x squared is the sine of the function x squared. It's important to take note of this in order to proceed. And also remember that we cannot go back up here. We cannot isolate this by itself and think of it as this times x, because the notation sine squared without the x is mathematically meaningless notation. Both of these terms will require the chain rule, and we proceed to do them one at a time. Okay, the first term is the square of sine of x. Here the inside function is sine of x. The outside function is just the square function, like this. The chain rule says the derivative of the outside, u squared, times the derivative of the inside. Derivative of u squared is 2u. Derivative of sine x is cosine x. So putting the u back in here, here's the u. We get 2 sine x cosine x, and that's the answer for the first term, square of sine of x. What about sine of x squared? In this case, the inside function is x squared, and the outside function is sine of x. You'll notice that it's just the opposite of the previous problem. But the chain rule applies the same way. Derivative of the outside function here, which is sine u, times the derivative of the inside function, which is x squared. Derivative of sine u is cosine u. Derivative of x squared is 2x. And since u is x squared, we put that back in, and we get 2x cosine of x squared as the derivative of sine of x squared. Then we add the two answers to get the derivative of the total and the answer to this problem. Alright, next let's take the derivative of ln of x squared. The chain rule is fairly straightforward. The inside function is x squared and the outside function is the natural logarithm. So according to the chain rule, we have the derivative of the natural log with respect to u, and then times the derivative of the inside function, which is derivative of x squared. Derivative of natural log log of u with respect to is 1 over u. Derivative of x squared with respect to x is 2x. If I put the u back in, I get x squared at the bottom, and 2x times 1 is 2x. Notice that I get a cancellation, and I'll be left with 2 over x as the answer to this problem. It's something that I need to say. There's one more thing I need to say here, that in problems involving the natural logarithm, sometimes it's easier to do these problems by doing a little bit of simplification at the beginning. And in this particular case, we could actually avoid using the chain rule. If instead of log of x squared, we simplify using a property of logarithm by putting the 2 outside and get 2 ln of x, then there is no inside-outside function. Derivative of 2 ln of x is simply 2 times the derivative of ln of x, which is 1 over x, and of course that's 2 over x, the same thing that we discovered using the chain. So it pays, if you notice it, it pays to simplify first. Now in this problem I have something for you that actually makes it a really good idea to simplify first before taking the derivative. If I try to use the chain rule right off the bat and looking at this whole fraction as the inside function, then to take its derivative, which is one of the 2 parts of the problem, I would have to use the quotient rule, and that's kind of messy. So instead, I take a closer look at the logarithm and see if I can break this up using properties of logarithm. Logarithm of a fraction is, of course, the difference of the logs. So let's use that property and get break up like this, the difference between the top and the bottom. And we know by the other property of logarithms, I can bring the 2 out and write it ln of x squared as 2 ln of x. And now I've gotten a much simpler expression, and I can move the chain rule without using the quotient rule. You'll notice that there is no more fractions. Okay, now that we have the simpler problem, let's take the derivative. The first function doesn't even need the chain rule, but the second function, there is an inside function for ln of x cubed plus 1. So let's use the chain rule on that. I'll get the derivative of ln of u. The outside is ln of u. So derivative of the outside times the derivative of the inside. Derivative of ln of u with respect to u is 1 over u. Derivative of x cubed plus 1 is 3x squared. The first term simply is 2 over x. 2 times the derivative of ln of x is simply 2 times 1 over x, or 2 over x. Next, let's put in the u in here and get 3x squared over x cubed plus 1. We can also combine terms using just a straightforward algebra to get a more compact answer that you see here for the problem. For our final problem, we take the derivative of ln of x. Here, both the inside and outside functions are the natural log, just the same function. And the chain rule then tells us derivative of the outside, 1 over u, times the derivative of the inside, 1 over x. Of course, notice that we are taking the derivatives with respect to different variables, and we get, after inserting the u back, we get 1 over ln of x times 1 over x, and then we multiply out, compactify 1 over x ln of x as the answer to this problem. And that is going to do it for us.